Hello and welcome to this video for CE 105-205. So in this video we are going to continue talking about topological constraint theory, but this time we're going to see in practice how to apply it to predict the glass forming ability of a certain substance. So as a summary of the previous video, the idea of topological constraint theory is to look at the structure of a given glass to predict whether this substance, when cooled, will tend to form a glass, to vitrify, or to turn into a crystal, to crystallize. And the idea behind this is to look at how many constraints, how many mechanical constraints are applied between the atoms that are forming the network. And so the main idea behind this is to count how many bond stretching constraints, so the constraints that are between pairs of atoms, which acts as a little spring like this that fix the distances between the atoms. Then to also count the number of bond bending constraints, where in this case those are the constraints that keep the angle between triplet of atom fixed. Once you have this, then you can calculate the total number of constraints and to look specifically at the number of constraints per atom, small nc. This is the number of BS and BB constraints per atom. And based on this, so there is different cases. If the number of constraints is close to 3, number of constraints per atom is close to 3, then you have an isostatic structure where the number of constraints is equal to 3. The number of constraints per atom is equal to 3, where 3 is also the number of degrees of freedom of each atom. Each atom can move, can be translated along the XYZ direction, so it has 3 degrees of freedom. So number of constraints equal 3 means that you have exactly enough constraints to counterbalance all the degrees of freedom. That gives you an isostatic structure. This is where you will have an optimal glass forming ability. So when the system has a number of constraints per atom equal to 3, this is where it's going to be the easiest to form a glass. On the other hand, if the number of constraints is lower than 3, then you end up with a flexible system where you have fewer constraints than degrees of freedom. So you would have some internal modes of deformation. In this case, you will have a lower glass forming ability. It's going to be easier to form a crystal, less easy to form a glass. And on the other hand, if the number of constraints is larger than 3, now you have more constraints than degrees of freedom. So you will have some constraints that are mutually redundant. And in that case, the system will exhibit some internal stress because all the constraints cannot be simultaneously satisfied at the same time. So you will have some of the constraints that will be elongated, some of the constraints that will be stretched. So in that case, this is also going to reduce the glass forming ability. So you will have a lower glass forming ability if the number of constraints is lower than 3 or higher than 3. This is where it's going to be easier to form a crystal. So the optimal cases is when the number of constraints per atom is equal to the number of degrees of freedom per atom, that is to say 3. This is when you have an isostatic structure. This is where it's going to be the easiest to form a glass. So now what we are going to see is to see how to apply this, how to count constraints in various types of glasses, and to see how we can use that to predict whether those systems will form a glass or not. So let's see a first example with the B2O3 system. So we know that this B2O3 is an excellent glass former. It's very easy to form a B2O3 glasses. We know that B2O3 satisfies the Zachariasen rules. So now let's see whether we can indeed confirm the fact that this system has a good glass forming ability based on the topological constraint theory. So for this, what I would recommend to count the constraint within a certain glass, I would recommend to construct this in terms of a table that will summarize for each type of elements how many constraints they are creating. That will summarize the constraints enumeration. So for this, in the case of B2O3, you have 2 elements. So you have boron and oxygen. So those are going to be the 2 lines within the table. Then in the first column, you can put the stoichiometry. You can put the number of those 2 types of elements. So for example, in this case, for every time you have 2 boron, you have 3 oxygen. So that's the stoichiometry. It's the number, the relative number of each types of elements within the glass. Next column would be the coordination number. So in this case, boron is threefold coordinated. So boron has a coordination number of 3. Oxygen is twofold coordinated. So it has a coordination number of 2. So this is going to be the coordination number. That's important to have the coordination number, which is R, because this is going to give us the number of bond stretching and bond bending constraints created by these elements. So in this case, the formula is that the number of bond stretching constraints is given by R to the power 2. This is the coordination, sorry, R divided by 2, coordination number divided by 2. Every time you have one boron atom, it's going to create, it has a coordination number of 3. It's going to create 3 bonds with some its nearest neighbor oxygen, but those bonds are also shared with the oxygen. So to avoid counting those bonds 2 times, we divide this number of constraints by 2. So the coordination number divided by 2 gives you the number of bond stretching constraints. So in the case of boron, coordination number is 3 divided by 2. That gives you 3/2. In the case of the oxygen, you have coordination number of 2 divided by 2, so that gives you 1 bond stretching constraints per oxygen atoms. So next, you have the bond bending constraints. So this, in this case, the number of bond bending constraints is given by 2r minus 3, 2 times the coordination number minus 3. So for example, in the case of the boron, you have 1, 2, 3 bond bending constraints. That's 2 times r, so 2 times 3 minus 3 equals 3. In the case of the oxygen, you have only 1. It has a coordination number of 2. So ça fait 2 times 2 minus 3 equals 1. So you have only 1 bond bending constraints. So you will have 3 here bond bending constraints for each boron and 1 bond bending constraints for each oxygen. So then, based on this table, you can summarize here for each element what is the total number of constraints created by each element. So in the case of boron, you have 3/2 bond stretching and 3 bond bending. So the total number of constraints would be 3/2 plus 3, which gives you 9/2. So 3/2 plus 6/2. So 9.5. And in the case of the oxygen, so you have 2/2 equal 1 plus 1. So that gives you two constraints. Total number of constraints per oxygen is 2. And now the last step is, once you have this, if you want to calculate the number of constraints per atom, all you have to do is to take the number of constraints created by each element times the number of these elements divided by the total number of elements that you have. So for example, in this case, you have 9/2 constraints per boron, and you have 2 boron, plus 2 constraints per oxygen, and you have 3 oxygen. That's the number of constraints per formula unit. But what you want is the number of constraints per atom. So you have to divide by how many boron you have and how many oxygen you have. So that gives you the number of constraints per atom. So in this case, we find that this is equal to 9 plus 6 equals 15 divided by 5. So you find 3 constraints per atom. So the number of constraints per atom in B2O3 is equal to 3. And so this means that indeed, as expected, you have an isostatic glass where the number of constraints is exactly equal to the number of degrees of freedom. And so this is another viewpoint that tells you that indeed B2O3 is going to be an excellent glass former. It's very easy to form a B2O3 glass. It's because it has an isostatic structure where the number of constraints is exactly equal to the number of degrees of freedom per atom. Next example is silica, SiO2. So again, we know that SiO2 is a good glass former, so we should expect also to find that this glass is going to be a good glass former with an isostatic structure. So let's start to do the same table. So you have silicon, you have oxygen. So same thing, you start initially by the stoichiometry. the number of each types of element. So 1 silicon, 2 oxygen, that's the stoichiometry. Coordination. Coordination number of silicon is 4. Coordination number of oxygen is 2. So based on that, now, based on the coordination number, we find the number of bond stretching constraints. So for silicon, it's going to be coordination number divided by 2, that gives you 2. For oxygen, it's 2 divided by 2, so that gives you 1. Bond bending constraints. So this is 2r minus 3. So in this case, once you have the coordination number that allows you to find the bond stretching and the bond bending constraints. So in the case of silicon, silicon has a coordination number of 4, surrounded by 4 oxygen atoms. So it's forming the 4 bond stretching constraints that are divided by 2 because they are shared with the oxygen. And it's going to form 5 angles. 5 angles, that are the 5 angles that are needed to define the tetrahedron. That's what you find with the formula 2r minus 3. So you have 5 bond bending constraints. Okay, and next, now we need to find out how many constraints are associated to the oxygen. How many bond bending constraints do you have? So typically here, you would typically put 1 because coordination number of the oxygen is 2, so that gives you 1 angle. Here there is one exception in the case of silica, is that silica has a very high glass transition temperature. So silica is forming at elevated temperature, and at this temperature here, this angle is thermally broken. Due to the high temperature, the bond associated to this angle is typically have an energy that is low as compared to the thermal energy that you have at such an elevated temperature. And usually it means that in this case, for this glass, and that's pretty much the only cases where you will see that kind of phenomenon, since this glass has such a high glass transition temperature, this constraint becomes thermally broken. So it means that this angle here, the angle between silicon tetrahedron, the angle around the oxygen, will have a great variability in silica. This angle is not fixed. It can have a very wide range of possible values. The angle around the silicon, this one is associated to a much higher energy, so this angle remains fixed. It's going to be close to 109 degrees, but the angle around the oxygen is not fixed. So this one, in this case, is not counted. And in this case, that's going to be pretty much the only kind of anomaly, or the only kind of exception to this rule in this case, where the oxygen, the number of bond bending constraints for the oxygen would not be given by 2r minus 3 in this case. The only exception would be silica, because it has such a high glass transition temperature. So now let's finalize the enumeration by counting the number of bond bending plus bond stretching. So you find 7 for the silicon and 1 for the oxygen. And now same thing, we can calculate the number of constraints per atom by calculating the number of constraints per silicon, which is 7, times the number of silicon, which is 1, plus number of constraints per oxygen, which is 1, times the number of oxygen, which is 2, divided by the total number of atoms, which is 1 silicon and 2 oxygen. So that gives you the number of constraints per atom. So in this case, we find 7 plus 2 equal 9 divided by 3. Again, you find 3. So in this case, again, we find that for silica, the number of constraints per atom is equal to 3, which means that, again, despite the fact that silica has a very different structure than B2O3, it has also an isostatic structure due to the fact that this angle here, this silicon-oxygen-silicon angle, is thermally broken at elevated temperature. You also end up with an isostatic structure, which is in agreement with the fact that silica has an excellent glass forming ability. It's very easy to form a silica glass, and it's very hard to form a SiO2 crystal. The next example is P2O5. Again, we know that P2O5 is a substance that is easy to form a glass. So again, we should find that the number of constraints per atom should be equal to 3. So let's see what we get. So in this case, as a reminder, the structure of P2O5 is that the phosphorus atoms are 4-fold coordinated. And in contrast with SiO2, in the case of the P2O5 glasses, around each phosphorus atoms, there is one oxygen that is a terminating oxygen, an oxygen that is not connected to any other phosphorus, while the 3 others are some bridging oxygen. They are connected to another phosphorus atoms. So that's the basic structure of P2O5. So let's see the usual table. So we start with phosphorus. Now we have oxygen, and so we are going to populate this table. So first column, the stoichiometry. So in this case, the number of phosphorus is 2, and you have 5 oxygen atoms. Next column, you need to provide the coordination number. So the coordination number of phosphorus is 4. And now you need to provide the coordination number of the oxygen. So here we have a first difficulty, which is that in this case, the coordination number of the oxygen is not fixed. You have a combination of those bridging oxygen atoms that have a coordination number of 2, but you also have some terminating oxygen that would have a coordination number of only 1. So here, what we typically do in this case is that rather than considering the oxygen, we are going to consider individually the 2 different types of oxygen that you can have. So we are going to individually consider the bridging oxygen that are in red in this structure, and also the non-bridging oxygen, the oxygen that are terminating, the oxygen that are connected to only 1 phosphorus atoms. So in this case, the bridging oxygen would have a coordination number of 2, while the non-bridging oxygen will have a coordination number of 1. So in this case, in the structure of P2O5, every time you have 1 phosphorus atom, every phosphorus atoms will contain 1 non-bridging oxygen. And this non-bridging oxygen is terminating, so it's not shared with any other phosphorus atom. So if you want to know the total number of non-bridging oxygen that you have, it's equal to the number of phosphorus in the glass. Every time you have 1 phosphorus, it's attached to 1 terminating oxygen, 1 NBO. So in this case, if you have 2 phosphorus, then you have 2 NBO, which means that in return, you will have 3 NBO, so that the total is 5. The reason that you have 3 NBO, for example, if you look at this structure here, you have those 2 oxygen here. So every time you have 2 phosphorus, like in P2O5, then you will have those 2 NBO, and you will have 1, 2, 3, 4, 5 oxygen. 1, 2, 3. You will have 1, 2, 3, 4, 5 oxygen atoms. But so this oxygen atom here is fully contained in between the 2 phosphorus atoms. But those oxygen here, they are going to be shared with some other phosphorus atoms. So they should be counted only half. So that's the reason why you end up with 1 oxygen, 1 half, 1 half. So that's another oxygen, and 1 half, 1 half. That's another oxygen. So you end up with 3 oxygen per formula unit of P2O5. So in each formula unit of P2O5, you have 2 phosphorus atoms. Each of those phosphorus are attached to 1 NBO each. So you end up with 2 NBO, and you have 3 BO atoms, 1 that is in the middle, and 4 that are shared with other formula unit of P2O5. So you end up with 3 BO, so that the total number of oxygen is indeed 5. 3 BO, 2 NBO. So now that we have this, we're going to just pretend that those BO and NBO, they just act as 2 different types of elements. Now we forget about the oxygen, we only consider the BO and the NBO, and in this table, we are just going to consider them as 2 different types of elements, just like if they were 2 different types of atoms. So next step, now that we have the coordination number, now we can add the bond stretching constraint. So since phosphorus has a coordination number of 4, that's going to give you 4 divided by 2, so 2 bond stretching constraints. NBO would be 2 divided by 2, BO would be 2 divided by 2, NBO is 1 divided by 2. Now bond bending, this is given by 2R minus 3. So for phosphorus, it's 5, just like silicon. Those are the 5 angles to define the tetrahedron. Next, boron. So it has, bridging oxygen. It has a coordination number of 2, so it would have 1 bond bending constraints. And NBO has only a coordination number of 1. So in that case, you cannot form any angle. So the number of bond bending angle would be 0 because it has a coordination number of 1, so you cannot form any angle. In this case, the formula here 2R minus 3, it only works where R is larger or equal than 2. If R equal 1, then this formula would not work, because if R equal 1, then you cannot form any angle. Okay, so now we can calculate the number of bond stretching plus bond bending. So we have 4 divided by 2 plus 5. So that gives you 7 for the phosphorus atoms. We have 1 plus 1 equal 2 for the BO, the bridging oxygen. And we have 1/2 for the non-bridging oxygen. So now we can calculate the number of constraints per atom. So we have 7 constraints per phosphorus, and we have 2 phosphorus atoms, plus we have 2 constraints per bridging oxygen, and we have 3 bridging oxygen per formula unit, and then we have 1/2 a constraints per NBO, and we have 2 NBO. And now we need to divide by the total number of atoms to get the number of constraints per atom. So we have 2 phosphorus, 3 BO, 3 NBO. So now based on that, that gives us 7 times 2, 14 plus 6, so 20 plus 1, so 21 constraints per formula unit. And we need to divide by the number of atoms, which is 2 plus 3, 5 plus 2, 7. So you have 21 divided by 7. Again, you find 3. So again, you find that the number of constraints per atom is equal to 3 again, despite the fact that, again, P2O5, B2O3, SiO2, all those glasses have very different structure. They are all isostatic. They all have a number of constraints per atom that is equal to 3, which is an agreement that those systems will easily form glasses. They will easily vitrify. They have a very good glass forming ability. Next example is would be a sodium silicate glass. So now it's not a single binary glass where you have some cations connected to some oxygen. Now we have a glass that contains 2 oxides. So that's another advantage of topological constraint theory, is that, for example, the Zachariason rules, that's only gonna work when you have a binary oxides, a cation A connected to some oxygen O. But for topological constraint theory, it can also apply to alloys when you have a combination of different oxides. So in this case, we are going to consider the example of sodium silicate, where you have a fraction X of sodium oxides, and the rest, 1 minus X, is a silica. So same thing, let's start to build the table. So we have silicon. Now we will also have some sodium, and we will have some oxygen. So let's see how many atoms we have. So first steps is the stoichiometry. So now the difference is that in the previous glasses, the stoichiometry was fixed. You had like 1 silicon, 2 oxygen in silica, 2 boron, 3 oxygen in B2O3, etc. So this is going to be different now because the stoichiometry depends on X. So now the number of atoms will depend on X. So in this case, if you have a fraction of silica that is 1 minus X, it means that for silicon, you will have 1 minus X silicon. So that's the first thing. Sodium, you have X mole of Na2O, but each mole of Na2O contains 2 sodium, so you will have 2X sodium. Oxygen, so in this case, the number of oxygen, you have 2 minus 2x coming from silica, and x coming from Na2O. So in this case, the number of oxygen will be 2 minus 2x plus x, so minus x. That's the total number of oxygen that you have. So next step, we move to the coordination number. So in this case, silica, you have a coordination number of 4. Sodium. So if you remember the structure of sodium silicate, so in this case, each silicon has a coordination number of 4. It's surrounded by 4 oxygen atoms. And whenever you have sodium is going to form some non-bridging oxygen with it's every time you add one sodium, it's going to form one non-bridging oxygen. So this is an NBO here. So the number of NBO in the glass will be equal to the number of non-bridging oxygen. The number of non-bridging oxygen will be equal to the number of sodium. Each sodium creates one non-bridging oxygen, and the rest of the oxygen, those are the ones that are connected to 2 silicon. Those are the bridging oxygen. So in this case, the coordination number of sodium will be just 1 because it's connected only to the nearest non-bridging oxygen. So again, here we have a case where if you look now at the oxygen, you have different cases. You have the oxygen that are bridging and the oxygen that are not bridging. So again, it's going to be convenient to, rather than considering all the oxygen together, to separate them into bridging and non-bridging oxygen, because those two types of oxygen will differ. They will not behave in the same way. So the first step is to look at how many of those do you have. So here the idea is that each sodium will create one NBO. So the number of NBO is equal to the number of sodium. So you have 2x sodium, means that you have 2x NBO. And now if you want the number of BO, then, well, you know the total number of oxygen, you know the total number of BO. So if you take the total number of oxygen minus the NBO, number of oxygen minus the number of NBO, that gives you the number of BO. The oxygen can be either BO, either NBO. So if you take the number of BO plus the number of NBO, that should give you the number of oxygen. So in this case, oxygen minus the number of NBO gives you the number of BO. So the number of oxygen is 2 minus x, and then you add minus the number of NBO, which is 2x. So you find 2 minus 3x. So that indeed, if you sum the BO plus the NBO, you find the total number of oxygen, which is 2 minus x. So now when you look at the coordination number, the BO has a coordination number of 2. It's connected to 2 silicon atoms. The NBO has a coordination number also of 2, but this time it's connected to 1 silicon and 1 sodium. So the BO atom here would be connected to 2 silicon, and the NBO would be connected to 1 silicon and 1 sodium. Next step, bond stretching. So in this case, bond stretching, this is coordination number divided by 2. For silicon, that's going to be 2. For sodium, that's going to be 1/2. For bridging oxygen, that's going to be 1, so 2 divided by 2. For NBO, that's also going to be 1. Bond bending. So let's do it. So in this case, silicon coordination number of 4, that gives you 5 bond bending. Sodium has a coordination number of only 1, so there is 0 bond bending. It has a coordination number of 1, so you cannot form any angle around sodium. Bridging oxygen. So remember, in the case of silica, we said that bridging oxygen has a broken bond bending constraints because of the fact that this glass has such a high glass transition temperature. But now, as soon as you have a little bit of sodium in this glass, the fact of adding sodium in the glass is going to dramatically decrease its glass transition temperature. Adding a little bit of sodium in the glass is going to drop its glass transition temperature. So now the glass transition temperature of sodium silicate glasses is going to be much lower than that of pure silica, which means that now the constraints here, the bond bending constraints between the silicon oxygen and silicon angle, this constraint is now going to be, should be counted just like any other constraints, because now these types of glass is going to be formed at lower temperature. So those constraints are now going to be active because the temperature is not high enough to break those types of constraints. So now I should put 1 because these types of constraints now should be counted. On the other hand, when you look at NBO, the difference here between the angle around NBO with respect to the angle of the BO is that the bonds forming by NBO and sodium is a network modifier glass. So sodium is forming some very weak bonds with the oxygen by definition of being a network modifier. And in that case, you have a very ionic bond that is very non-directional. So in the case of those NBO atoms, so these types of angle, the angle that is formed by the silicon, the oxygen, and the sodium, this angle is very weakly defined. There is a great variety in this angle because it's forming an ionic bond between the oxygen and the sodium, and this ionic bond is not directional. What the bonds that are directional are the covalent bonds, like silicon-oxygen. This silicon-oxygen angle is going to be directional. It's going to have a fixed value, but the bonds that are forming based on ionic bonds, those bonds are non-directional. So this silicon-oxygen-sodium angle should not be counted because it's not directional. This angle is not going to be fixed. It can have any value in the glass. There is no constraint that's going to force this angle to remain fixed to a given average value. So we should not count it in the constraints evaluation. So now let's summarize. So let's count bond bending plus bond stretching. So 7 for silicon. We have 1/2 for sodium. We have 2 for bridging oxygen, and we have 1 for NBO. And so in this case, this is really because those BO and NBO, they have a different number of angular constraints, a different number of bond bending constraints. This is really why you need to differentiate those two. You need to consider them as two different atoms. Otherwise, the number of constraints calculation would not be correct. So now, summary, number of constraints per atom. So you have 7 silicon, and you have 1 minus X silicon, plus, so 1/2 sodium, and you have 2X sodium. Next, 2 BO, and you have 2 minus 3X BO, and you have 1 constraints per NBO, and times 2X NBO, divided by the total number of atoms. So you have 1 minus X silicon, plus 2X sodium, and here either you can put the number of bridging oxygen plus the number of non-bridging oxygen, or you can directly put the number of oxygen, which is 1 minus X. So if we summarize here, so if we count the number of constraints, so the terms that do not depend on X, so you have 7 plus 4, so that gives you 11, and the terms that depends on X, so you have minus 7 plus 1 minus 6 plus 2, so that gives you 10x. This is the number of constraints per formula unit. You need to divide by the number of atoms, which is 1 minus x plus 2x plus 2 minus x. That gives you simply 3. So the number of constraints per atom in sodium silicate is given by this number, 11 minus 10x divided by 3. So in this case, you have a case here where the number of constraints per atom, here it depends on x, because depending on the value of x, depending on how much sodium oxides you have in the glass, well, that's going to change the average number of atoms that you have that have different coordination numbers. So that's going to change the average coordination number. Here, the average coordination number of this glass, it depends on x. The more you increase x, the more you add Na2O. Na2O breaks bonds in the glass. Na2O breaks some connection between the silicon. It's transforming some bridging oxygen into some non-bridging oxygen. So here, as you can see, if you plot the number of constraints per atom as a function of x, that's going to be a function that linearly decreases. The more you increase x, the more the number of constraints per atom decreases. It's because sodium atoms tends to depolymerize the system. So now what you can check here is you have this number of constraints. It depends on x. So here the question is, can we find the stoichiometry, the sodium silicate glass that's going to have the maximum glass forming ability, the sodium silicate glass that's going to be the easiest to make. So for this, we need to check when is the number of constraints is equal to 3. We know that number of constraints is equal to 3. That's the isostatic condition. That should be when the glass has the maximum glass forming ability. So based on it, you just have to solve for which x, which is going to be a specific value of x, where x is equal to the is going to correspond to the isostatic threshold. So I'm going to solve this equation. What is the value of x that gives me a number of constraints per atom equal to 3? And I want to find the specific value of x that I'm going to call x iso. That's going to give me the composition of the isostatic glass. And so in this case, if you find this, so that gives you that x iso, so you can invert this this equation, and that you find that x iso is going to be equal to so 11 minus 6, which is 5 divided by 10, so that gives you 0.2. So 0.2 here is the fraction of sodium oxide that's going to give you an isostatic glass. It means that when you have 20% of Na2O and 80% of SiO2, this is where you will have an isostatic glass. So this types of glass with 20% sodium oxide is going to be, in this case, the optimal glass former. This is the case where the glass is going to have the maximum glass forming ability. If you have less sodium than that, if x is lower than that, then in that case, if x is lower than 0.2, then you would have a number of constraints per atom that is larger than 3. So you would have a stressed rigid glass, which would easily either crystallize or phase separate. So it would have a low glass forming ability. And if x is larger, and typically much larger than 0.2, then you would have a number of constraints that is much lower than 3. And now that's going to give you a very flexible glass. And these types of glass that would be very flexible would have a low glass forming ability. So typically in these types of glass, you can still form a glass anywhere between x from 0.2 to up to 0.4. But any x that is much larger than 0.4 would give you a glass that becomes too flexible, where the number of constraints is too low as compared to 3. And in that case, you would have a very low glass forming ability. It would very easily crystallize. So that's one example where, in this case, you can use topological constraint theory to find the range of composition, or at least the composition that's going to give you the maximum glass forming ability. Last example would be a chalcogenide glass, a germanium selenium glass, where you have a combination of a fraction x of germanium that have a 4 neighbors, a coordination number of 4, and the rest, 1 minus x, is selenium. So same thing, we do the usual table. So you have germanium and selenium. You put the stoichiometry, so the number of each element. In this case, again, the stoichiometry is going to depend on x. So you have x germanium, 1 minus x selenium. Coordination number. So in this case, each germanium has a coordination number of 4. That's what you get by the A minus N rule. Each selenium has a coordination number of 2. Bond stretching constraints. So 5 for germanium, just like silicon atoms, and 1 for selenium, just like oxygen atoms. Bond bending. So you find, sorry, let me start again. The number of bond stretching, this is given by R divided by 2, so that's equal to 2 for germanium, and for selenium it's 2 divided by 2, so that's 1. Now we move to the bond bending constraints. So you have 5 for the germanium, just like the silicon, that's 2R minus 3, and for selenium you find 1, which is the angle around the selenium, the angle formed by selenium and its two neighbors. Bond stretching plus bond bending. So you have 7 for silicon, 2 for selenium. So now number of constraints per atom. So you have 7 constraints per germanium times x germanium plus 2 constraints per selenium times 1 minus x selenium divided by the number of germanium, which is x, plus the number of selenium, that is 1 minus x. So that gives you 7x. So the terms that do not depend on x would be just 2. The terms that depend on x would be 7 minus 2, that is to say 5x. And you divide by the number of atoms, but in this case, number of atoms is just equal to 1. So in this case, you find that the number of constraints per atom is equal to 2 plus 5x. So now it means that if you look at the number of constraints as a function of x, now it's going to be a function that is linearly increasing with x. It means that the more germanium you have, the larger x, the larger is the average coordination number. It's because as you increase x, you are gradually replacing some selenium that have a coordination number of only 2, and you are replacing them by some germanium that has a coordination number of 4. So if x equals 0, so the number of constraints would just be 2. That's what you would find for pure selenium. Pure selenium has 2 constraints per atom. But as you increase germanium, this number is going to increase because germanium has a higher coordination number, so that would increase the average number of constraints per atom. So same thing, now you can look at what is the optimal alloy, what is the composition here, what is the optimal stoichiometry for this germanium selenium glass for which you will have maximum glass forming ability. So for this, you need to solve what is the number of for which x will you get an isostatic glass, that is to say a number of constraints equal 3. So for this, you need to solve 2 plus 5x. You need to find the value of x that's going to give you a number of constraints equal to 3. And so in that case, you find that this condition would be satisfied if the x iso is equal to 1 divided by 5, which gives you, in this case, a concentration for germanium, which is 0.2. So in this case, if you have 20% of germanium, and in this case 80% of selenium, this is where you will have an isostatic glass. In this case, a glass that would have an isostatic structure with an average number of constraints is equal to 3. So if you want to find, in this case, what's the composition of this glass, so we say that it's 20% germanium, so there's various ways you can write this. So you can say 20% germanium, 80% selenium, so that's one way, or you can write it G2SE8, so that's another way, that's the same thing, or you can write it GSE4. Those are equivalent stoichiometry. Every time you have 1 germanium, you will have 4 times more selenium. So typically, you will write this glass as GSE4. So GSE4, in this case, would be the composition where you have the optimal glass forming ability. So if you summarize as a function of x, if you look at the value of x, so x can go between 0 to 1, but if you look more specifically as a function of x, so if x equals 0, then you would have pure selenium. That would be a glass that would have only 2 constraints per atom that would be flexible. At x equal 0.2, this is where you have the isostatic transition. This is where the glass becomes exactly isostatic. Number of constraints is equal to 3. So anything before that, between 0 and 0.2, this is where you have a flexible glass. This is where number of constraints per atom is lower than 3. And anything x between 0.2 and 1, this is where you have now a stressed rigid glass, where the number of constraints per atom would be larger than 3. So those are the 3 possible cases. In this case, as a function of x, the glass can be either flexible when you have either no germanium or a very low amount of germanium, can be stress rigid if you have a lot of germanium or if you have no selenium at all, and when you have exactly 4 selenium for each germanium. This is the optimal case. This is where you end up with an isostatic glass, number of constraints equal to 3. This is where you will have the optimal glass forming ability. So you can do also this calculation for all the types of chalcogenide glasses. Like for example, if you have an arsenic selenium, you can also determine what's the optimal composition that will give you an isostatic structure. So that's the interest of the topological constraint theory. It doesn't apply only to binary oxides like the Zachariasen rules or the Sun's criterion. It works for alloys of oxide glasses like sodium silicate, or it works also for other types of systems like chalcogenide glasses. So in that case, it has a broader range of application than the Zachariasen rules only. It's equivalent to the Zachariasen rules, like we also find like that silica, B2O3, P2O5, all those glasses that are predicted to be good glass former by the Zachariasen rules, they are also predicted to form glasses easily based on topological constraint theory. But topological constraint theory in this case has a wider range of application. It can apply to other types of glasses that are not covered by the Zachariasen rules.